Thank you for waiting. My name is David Madlener. I am the chairman of FAR, in German Forschungsgemeinschaft für Raumfahrt. That's in English. Well, we are researchers. We research alternative space travel. And today, as I heard that you hackers want to go into space, I thought, well, maybe I just come by to Finofurt and tell you something we normally do all day, so you can estimate how complicated or easy it is to go to space. So my little lecture will start with a short introduction, showing the beginnings of space travel and some of the fundamentals you need before starting to go to space. Then we will talk about little propulsion basics. This will be at the basic level, but there will be some formulas, so please don't go away. You just have to use them. You don't have to deduce them. So it's not that difficult. So, and at last I will talk about technologies we can employ today, very shortly. There will be more talks in the following days about solid rockets and hybrid rockets and our program, so I won't go too much into detail in the third part. Okay, let's start with introduction. So first of all, when I speak to people on fairs or when we meet with people that are not genuinely interested in space travel, they always ask us, why? Why do you do that? I mean, isn't it a waste of time? It's so much trouble to go into space, and what do you want to do there? Well, there are some arguments. And the first argument is just curiosity. Can we do it? Is it possible? And if it's possible, what will we find? So, of course, curiosity kills the cat, so this is not the only argument you should pursue. And the next one is exploration. Of course, this is very near to curiosity. So we can go out to other worlds, travel there, look what's there, explore, maybe bring something back, learn something about the universe. And very importantly, as we have seen from many programs that have been conducted in the past, I mean, without Apollo we wouldn't be sitting here, technology is a major driver in space travel. It is, of course, first are the problems, then you solve them, and then there are some spin-offs. And there are numerous, so much spin-offs that we can't count them. The only spin-off that everybody knows is not a spin-off, the Teflon. It's not from rockets. Okay, but everything else, for example, personal computers, miniaturization, chips, etc. A lot of algorithms. So, and then on a more basic level, of course, science and philosophy. I myself, I'm normally an astrophysicist, so I'm very interested in stars. And our main problem here on Earth to look at the stars is the air. So every time you try to see something, the air is in the way. And you all know that the best images ever taken from a telescope were the images taken by the Hubble Space Telescope. And this is, of course, not due to the very large mirror. The Hubble Telescope has only a mirror of 3.2 meters compared to a very large telescope, for example, the Atacama Desert, the VLT, has over 8 meters. But there is no way that you can go to the resolution of the Hubble Space Telescope due to the missing air out there. So, of course, there are philosophical questions. For example, where do we come from? Is there a God? How did it start? Big Bang and so on. So that's a lot to do with space travel. But in my point of view, the most important point is survival. Not on the short term, I hope, but on the long term. Because if you look at the evolution on Earth, we know one thing for certain. More than 99.99% of all species that existed on Earth are extinct. So why wouldn't we go extinct? It's just a matter of time. There are so many things that could happen in the future, and if you go out there in space and learn how to survive, that would be the best way to survive on the long term. And of course, we can go out there to colonize. I won't talk about these things in special today. I will only talk about the technology, how to do that. But you always have to keep that in mind. One of these things must motivate you to do this. Otherwise, leave it. Because engaging in space travel is A, very dangerous, B, it costs a lot, 3, it can be very frustrating, and 4, everybody looks at you and says, why are you doing this? It makes no sense, okay? So, but they were pioneers. And one of the pioneers, he's called the father of rocketry, Mr. Goddard, had an epiphany. In 1899, to be exact, on 19th of October, sitting on a cherry tree. He was going out there to cut the tree, in fact, but he had read a book named War of the Worlds from H.G. Wells. And while he climbed the tree, he later wrote, "It was one of the quiet, colorful afternoons of sheer beauty which we have in October in New England, and as I looked towards the fields at the east, I imagined how wonderful it would be to make some device which had even the possibility of ascending to Mars." Remember, this is 1899. There were no planes, okay? And how it would look on a small scale if sent up from the meadow at my feet. And later he wrote, "I was a different boy when I descended the tree from when I ascended, for existence at least seemed very purposive." And this 19th of October for him was a very special day, and every year he put in his calendar, okay, today is 19th of October, I did something special. And some years later he would achieve something special. So if he was a father, then this was a grandfather of rocketry, Mr. Tsiolkovsky, who was a school teacher somewhere in Russia, and he had this crazy idea that one could go to space. And he was doing this in 1800, I don't know, 60, 70 or so, calculating in his room. Nobody even mentioned it. He was an old, weird man. So in 1903, he published a paper in a Russian journal called Exploration of Space with Reactive Devices, and these were his main points. That space travel is feasible, that rocket propulsion is needed to move through space in vacuum, there's no air, and that gunpowder is not the way to go because it has not enough energy. And he mentioned that there are liquids sufficiently energetic to do it, and he even mentioned the combination liquid oxygen and liquid hydrogen. This is very remarkable because liquid oxygen was only available on an industrial scale from 1895, so 8 years prior. And liquid hydrogen had been synthesized in a quantity of 5 liters in, I think, 1898. So these were very exotic materials and nobody was talking about them. This was high-end research. So Mr. Tsiolkovsky published this paper. Some may have read it, nobody understood it, nobody responded. So he was way ahead of his time. Then again, Mr. Obert, a German, tried to make a dissertation in 1922. I think it was in Göttingen, and he introduced it to his professors, and they read it, and no one understood it, so they didn't give him his PhD. So he rewrote it, went to another university, and entered it as a diploma thesis, and it was accepted. And later, in 1923, or the same year, he published this revolutionary book, The Rocket to Planetary Spaces, or in German, Die Rakete zu den Planetenräumen. And in this book, he said, it is possible to build devices that can beyond the atmosphere. It's very clear to the lines that Tsiolkovsky made. And these devices will reach velocity to leave Earth, and even with human beings. And very important, he showed that it was feasible, that in a few decades, with the technology at hand, and if the economic circumstances were favorable, it was possible to build such large devices. So from this, there came a lot of action, especially in Germany, here in Berlin. There was a Verein für Raketenkunde, VFR, and Mr. Obert was one of the founding fathers, and one of the members was Werner von Braun. And later, Werner von Braun went to America and built a Saturn V that went to the moon, and Obert was then one of his colleagues. So, by the way, this photo was taken in 1929 in the UFA cellars, where he was building a rocket. So they made a movie called The Woman in the Moon, and it was so successful that they gave him money so he could build his own rockets. So this was the time then where film industry pushed science. Yeah, long ago. So, 26 and a half years later, Mr. Goddard in the meantime, he was a renowned physicist, a professor at Clark's University, built the first ever known bipropellant liquid rocket. And it wasn't very impressive at the time. Well, it flew on gasoline and LOX, so he used liquid oxygen like Tsiolkovsky proposed. The tank, low below the burning chamber, so that's not very good visible. The upper device is the burning chamber, and the lower device contains the gasoline and the liquid oxygen. So it's kind of, from today's use, unorthodox, but he thought at that time that this would be favorable to his experiment, but he later reviewed that. So he used for the first time the Laval nozzle, which never had been used before. And his rocket had a specific impulse, we'll speak about this later, of 170 seconds. That's not very impressive for such a device, but surely he reduced the temperature of the burning chamber to improve the cooling, otherwise it would have burned through. So the flight itself wasn't very impressive. It got to 56 meters, so not well out of sight, and it only went for 2.5 seconds. There was a camera running at the time, but the rocket didn't lift off, and when the rocket finally did lift off, the camera had run out of film. So unluckily, no images from this first flight. So let's talk about reaction engines in general. This is an abstract view of how reaction engines work. We have a propellant that is normally in a storage. Then we have a feed system, and this feed system moves the propellant to a so-called accelerator. And the accelerator needs energy, so we need an energy storage and some kind of converter that runs the accelerator. So this is the principle on which every reaction engine we ever built works. So, propellants, there are a lot of propellants. We have tried nearly everything what can burn, even what can't burn. So they can be, in principle, gaseous, liquid, or solid. Nowadays, it's normally used liquid or solid phases. The gaseous phase is not very advantageous, only in some special cases because the density is very low. So you have to build very large vessels. And you can use one or multiple propellants at a time. Normally it's one or two, but there are also engines that use 3 propellants. And depending on the concept of the engine, it may or may not contain energy. So if it's a chemical internal combustion engine, the propellants have to contain energy. But if it's, for example, a nuclear rocket, the energy is brought somewhere else into the mix. So, and the propellant, and this is the main function, is the medium for momentum exchange. We'll come to that later. It's the main principle, the principle of recoil. So, and if the phase is not liquid, not solid, then we need a storage to hold the propellant, otherwise it would just, I don't know, fall out of the rocket. It's trivial, but it's necessary to think about that. So, energy sources, what is there in principle? So there's, for example, the inner energy of some compound. Normally a gas, a very high pressure like helium or hydrogen or nitrogen, whatever one chooses, depends on the operation. It can be a chemical reaction. So we have normally a very potent oxidizer with some stuff that burns, like kerosene or hydrogen or whatever, hydrazine. Then there could be electrochemical sources like batteries or fuel cells. This is especially for electrical propulsion, important. And it could be photoelectric. This is, by the way, Juno. It's not very well visible. That has been sent last week to Jupiter. And it has, of course, very large solar sails, as Jupiter is at 5 astronomical units. So it only reaches about 1/25 of the solar radiation we have here on Earth. So the solar panels have to be much larger, 25 times much larger than here on Earth to deliver the same energy. Then again, very effective nuclear fission is a very potent way of producing energy. The only problem is, well, it's not politically favorable, and it has some drawbacks due to the production and storage and so on of the energy source. And very temptative, but still not working, is nuclear fusion. It would be ideal because out in space we would have a lot of hydrogen, helium, and deuterium and so on. So we could, for example, go to Jupiter, make a fuel stop, take whatever we want, and then go beyond whatever. But that's not the time. And very interesting, in principle feasible, and it's at the moment underway, some investigation at, I think it's Stanford, the use of matter, antimatter annihilation. So you could use pure matter-antimatter annihilation, or you can induce by antimatter, for example, a fusion reaction or a fission reaction or a fusion-fission reaction. So you can use the antimatter as a catalyst, so to make the normally very difficult fusion reaction feasible. But this is still in the works, and we don't know. No? Just imagine 100 years ago there was one plane or so we don't know what is in 100 years here on Earth. Okay, let's talk about acceleration principle. They are not much. In essence, they are all electrodynamical. So there's gas expansion. That's a normal way to accelerate the propellant. And the Lorentz force, which is just the electromagnetic force, and you can use purely electrostatic force, or you can use a mixture, so you can use the Hall effect, for example. Okay, that's in principle what can be used to accelerate particles. Of course, there are other words for it. You can use photons, but in a sense, it's always electromagnetic. So let's talk about engine applications. So what do we use engines for? Well, there are some major functions. So this is a launch. That is, we are, for example, on Earth or the Moon, and we want to go up. Then we have orbit insertion, where we are already in a certain orbit and we want to reach another orbit. So we have to burn at an exact time, for an exact period of time, delivering an exact number of Newton seconds, otherwise we won't get to the orbit, so it's high precision. Then we have maneuvering, which is not so high precision, but also necessary to do, for example, if the International Space Station, due to the friction to the air, slows down, then you have to additionally move her up, otherwise it will crash down on Earth. This is a typical maneuvering application. And then we have attitude control, where you exert torques with the engines to turn the spacecraft around, to point it in a certain direction, or to spin it up to stabilize it for orbit insertion. And as important as launching, maybe landing. When you have no atmosphere, there is no other way than to use your rocket engine to land softly. Everybody knows the game, Moonlander, yes? And if you don't do it precisely, you will crash or just go away again. So these are the main function an engine has to perform, and normally every engine is specialized to its function. And there are very few engines that can master several of these functions. So for example, if you look at the spacecrafts that Armadillo Aerospace is building, then they have, of course, launch and landing, you have attitude control, and maybe a little bit of maneuvering, but certainly still not orbit insertion. So it's a multifunctional engine. So let's look at, from my point of view, best rocket ever, the Saturn V, that launched in the years from about 64, 63 to 73, no, 75 was the last time, in modifications. And this is the original version that launched to the moon in July 69. So we see mainly 3 stages. And as an illustration, do we have a pointer? No, we don't have a pointer. Okay, you can see below there, right, left to the nozzles, there are 2 people standing. It's about 1.80 meters. So the lowest 5 engines, the F1 engines, thank you very much. So, okay, so these engines here are still today the largest engines with a single chamber ever built. They deliver a thrust of 6.672 meganewton, which corresponds to about 670 tons of thrust each. So this monster here produces about 3,600 tons of thrust at liftoff. Of course, the whole rocket weighs just above 3,000 tons. So it accelerates very slowly with a thrust-to-weight ratio of approximately 1.2. So the lower stage ran on liquid oxygen here, and RP1, which is just kerosene for planes. And the engines, all of them together, combusted around 13, 14 tons per second. So just imagine what you could do with some tons of kerosene in your life, yeah, per second. So when this burned out, then the second stage, first these 8 Ullage motors with, well, 10 tons of thrust or so, separated the 2 stages. And then the 5 J2 engines started, and they have a thrust of around 90 tons. So these were used to hurl the Saturn V into low Earth orbit. And after burnout of this second stage, then there was a parking orbit, and then finally this J2 engine, a single engine, would hurl it to the moon. And the rest, you see very, very small things there. Everything you see there is an engine. So I didn't bother to enlarge everything, but because we would be talking hours here only about the Saturn V. So let's look at the mission. This was the Apollo mission. It's called LOR scenario. There were 3 scenarios that were selected to go to the moon. The first scenario was just lift off with a very, very large rocket, they called it NOVA, and land directly on the moon. The problem is, if you do that, then you have to take off a very large spacecraft from the moon and an even larger spacecraft from Earth, so it would be even more larger than Saturn V, about 3-4 times larger. So the second scenario was to take several smaller rockets and assemble a large rocket in Earth orbit and then go from there, from Earth orbit to the moon. The problem was that it was never tested to rendezvous such large devices in a low Earth orbit, so it was abandoned because it was too risky. And then there was a third scenario, like a shadow horse that started. Nobody paid attention at first, and this was this lunar orbit rendezvous. And this scenario was thought of by a Ukrainian in 1915. Sadly, I forgot his name. So the idea to do this is very old. It's about 50 years before they first attempted. So essentially, we launch at Cape Canaveral. Oh, this thing doesn't work. Yeah. So we launch. Come on. Can anybody see something? I don't see it. Okay, I just go here, over there, and show you. That's nonsense. So the launch starts here. Then we have burn off, the Ullage motors separate, and second stage starts, and then we enter into low Earth orbit. This is the parking orbit. So the Apollo mission always stayed a time on the parking orbit and checked the systems, everything was fine, because if something went wrong at this stage, then they just had to return. So then at this point, there was translunar insertion. That is the third stage. The single J2 motor would burn for a few minutes, and then send Apollo to a translunar trajectory. That is, if nothing else happened, it would just return by turning by the moon and going back. That's what happened to Apollo 13 when something went wrong. They just didn't go into lunar orbit, they just returned to Earth. So in this several stages starts what the engineers were worrying about, the rendezvous maneuver. So from the burnt out third stage, there was a small vehicle with the crew on board. This was the CSM, the crew and service module, and the lunar lander. But first, the crew and service module had to get out, then turn around, get back, make a rendezvous, and take the lander out. So it was very difficult. And this is done because the lander was very much broader than the crew and service module. So they couldn't put it in the correct configuration at start. Then after a while, I don't know, 2-3 days, they make a mid-course correction. And when they enter the lunar orbit, they have to make this lunar orbit insertion burn. It's very precise, has to be done at the exact moment. And then they entered into lunar orbit. And then the crew and service module stayed in lunar orbit, and at this point here, the landing module separated with 2 men on board and descended to the moon and landed. So this was essentially the trip in one direction. And then after making the experiments and walking around on the moon, they entered again the lunar lander. And the great advantage of this scenario is that when the lunar module, the landing module, ascends, it can leave behind a lot of mass. So it's again another stage, and it has to reach this 1.6, 1.7 kilometers per second to reach again the lunar orbit to rendezvous with the mothership. So that's what it did. It landed, then there was a rendezvous, and then they returned with a burn, trans-Earth insertion, then a mid-course correction. And then at this point, up there, the lunar lander was jettisoned, and the rest was aerobraking and splashing down. So this was essentially a scenario of Apollo mission. So a lot of engines were involved in that, naturally. So now that I've talked so many things about application and functions and what we can do with engines, I will go to the basics, and we'll talk first about the physical fundamentals of a reaction engine. So there's a well-known observation of physical law, the conservation of linear momentum. So if you are an inertial observer and you look at a system that is closed, that no forces are acting on it, then you see that the total momentum of the system is constant. So if we look at the rocket for one instant in time over a certain time interval, delta t, then there may be an ejection of mass in the opposite direction. So the system moves with a certain velocity v, and after some, or during a certain time delta t, a mass delta m is ejected in the opposite direction with some relative velocity I call here u. That's called the effective exhaust velocity. So if you look at this state before and after, you could write it down in a formula. And it's just this equation. So on the left side, we have the impulse, the momentum before, and on the right side after. And if you look close at it, nearly everything vanishes. So you can divide by the time interval and integrate, so you get to this equation. And by integration, we get to the celebrated Tsiolkovsky formula. So this is a formula that Tsiolkovsky found in the 19th century. Of course, nobody understood what he was doing. And it states that the change in velocity of a rocket that is propelled by a reaction engine is proportional to the velocity that the propellant is pushed outward, the effective exhaust velocity, u, and it's proportional to the natural logarithm of the mass fraction. So the mass fraction, this is very important, m0 divided over m1. This is the ratio of the mass before and after the burn. So if this is 1, so the mass are equal, nothing happened, ln of 1 is 0, okay, so there's no delta V. If you have a mass fraction of approximately 2.7, so Euler's number, then you have in this factor 1, so you have a delta V of exactly the exhaust velocity. And practically, you will try to achieve a mass fraction as large as possible, so this logarithm gets as large as possible, so your velocity is as large as possible. And that's a problem, because at the end of the burn, there's always something left. The rocket doesn't consist only of propellant. It consists of the engine, the accelerator, the feed system, the storage tanks, the cabin crew maybe. Yeah? So there's always some mass left. But before we go into staging, let's talk on the delta V budget. So delta V budget, that's what mission analysis always talk about. Delta V, delta V, delta V. It's very important because if you don't do this correctly, you never reach your target. So this is a graph showing possible routes starting here below at the Earth. And the most costly step, okay, except for going to the sun, but nobody does that at the moment, is going from Earth to low Earth orbit. That costs between 9 and 10 kilometers per second. That's a number one has to keep in mind. If you want to orbitalize anything, you have to reach this number, okay? So if you go to low Earth orbit after that, you can go, for example, over geosynchronous transfer orbit to lunar orbit in 4.1 kilometers per second. So not as much as half of that was used here. So in total, you need about 14 kilometers per second to reach lunar orbit, and then again about 1.6 kilometers per second to touch down softly on the moon. If you don't want to touch down softly, you need less. Okay. Of course, if you want to go up, you need the same amount, yes? By the way, the red arrows are aerobraking. So every time you encounter an atmosphere, you get delta V for free if you use the atmosphere to brake. Yeah? So if you go back, that's what Apollo did. They just had to take 1.6 kilometers per second to ascend the lunar module to the CSM, and then again about 1.6 kilometers to reach GTO or something like similar, and then the rest was done just by aerobraking. So you need a much smaller rocket to go from the moon back to the Earth than vice versa, okay? And that's why the moon is a perfect place to build a space base. Because, as the engineers designing Apollo did, it is very difficult to build something in Earth orbit. You know, we have the ISS and it's very, very big and everybody's talking about this, but the problem is it's zero gravity. Have you ever tried to assemble something in zero gravity? Don't do it. It's not possible. You cannot do fine things in zero gravity. They even lose their how it's called, the hammers and so on, just because they are not watching, and it just floats away. So normally if you work on difficult things, like we normally do, you need gravity because you want to put something down and it stays there, okay? And another problem one normally not bothers about is when you, for example, work on metal in microgravity. So for example, you turn a screw, you may be screwed because you will loosen some metal, and it will float away and make somewhere a short circuit. Maybe not today, maybe not tomorrow, maybe next week, okay? That's a problem you have in no gravity environment. So the next low gravity environment we have is the moon, and if we could assemble something there, we could go to the Mars much easier from Earth because 1.6 kilometers per second, and then about 0.7, and then about 4 kilometers per second and you're on Mars, okay? It's much easier, much easier. So, delta V budgets. Now about how to reach it. The problem is the effective exhaust velocity is normally not in the order of 10 kilometers per second, for example, to go to low Earth orbit, but in the order of some kilometers per second, 2, 3, 4, maximum 4.5, okay? So what you have to do to achieve higher end velocities, higher delta Vs, is to use staging. What was used with Saturn V with at least 5 stages. And what you effectively do is you burn off one stage, and then you jettison all the heavy stuff that is left, the engines, the feed system, the storage tanks, etc. Although they are very costly, but they are mass, and they would have been accelerated. So by jettisoning them, you effectively increase the mass ratio every time. So the only thing that counts is the starting mass and the end mass. So looking at the Saturn V, you start with about 3,000 tons, and you end with this little thing there up there with, I don't know, 30 tons, 40 tons or so. So you have a mass ratio of nearly 1 to 100, and then you can get to the moon. That's the problem why you have to build big rockets. So staging is very important. So we come now to a very basic part of rocket technology. It can be very exhausting, and so I don't want to bother you very much. I will just show you some formulas. Maybe you know them, maybe you don't. If you ever want to understand rocketry, you have to dive into it and read a thermodynamics book. There's no other way around it, okay? So, there are 3 basic laws in thermodynamics. I will only show you the first in a second. The first just says every system has an inner energy called U, and it can change due to the addition of heat, Q, or due to work, W. And the second law is just there is something called entropy, and we thermodynamicists don't understand what it is from a phenomenology level. Just if you put heat into a system at a certain absolute temperature, then this entropy increases by this amount. Okay, later on one can understand this from a different point. So there's a joke. The first law states you can't win, and the second law states don't even try. So, energy and temperature. So there are some things you should know before I show you some formulas. There's this Boltzmann constant you may have heard of, very small, 10 to the power of minus 23. And in every physical system that is composed of atoms and molecules, and everything is composed of atoms and molecules as far as we go, there are things they're called degree of freedom. So if you have a molecule, the molecule can move in space, x, y, z, so it has 3 degrees of freedom of translation, and it may rotate, let's say, 2 axes, like for example for a diatomic molecule, then it can rotate this way, or it can rotate that way, but this way is not so efficient, so it has 5 degrees of freedom. So, but every degree of freedom has always this amount of energy. So you can calculate in the mean, it will have this energy. This is called Boltzmann's Gleichverteilungssatz. I don't know what's in English. So then there's something, it's the heat capacity of a system. It doesn't matter what it is. If you put heat into it, it will change its temperature. And the heat capacity is just how many joule in heat you have to put in to increase the temperature by 1 Kelvin. So then you can define heat capacities as constant volume. You can define a quantity is called the enthalpy. And you can define heat capacity at constant pressure. And very important for the next following formulas is the adiabatic index. This is just the ratio of these 2 heat capacities. Of course, these may seem very strange if you have never seen these formulas before, but you just have to understand what they mean and fill in the formulas and you get out what you want. Okay, you don't have to understand what's really happening. But it will be better. So, if you look at chemistry and thermochemistry, then you need Avogadro's number, a very large number. It's a number with 23 following numbers. And if you multiply it with Boltzmann's constant, you get the so-called universal gas constant, which is approximately 8. Okay, and the amount of substance is just, you must think about the Avogadro number like a dozen. Yeah, okay, a very large dozen. It's not 12, it's just 6 and very much, a long number of numbers. And if you look at a batch of whatever substance it is, you could say, okay, this is so much dozen of molecules, and instead you say it's so much moles of molecules. There's no difference. So then you have molecular weight. That's very important for the exhaust velocity. The molecular weight is just the weight that 1 mole of the substance has. As for example, the normally known carbon, which is the definition, carbon-12 weighs exactly 12 grams per mole. And water, for example, weighs exactly 18 grams per mole. So depending on what comes out of the exhaust, this molecular weight will differ. It depends on what propellants you put in. So then the molar concentration, it's just how many moles there are in a volume. The number concentration, how many particles are in a volume. The mass density, how many masses in a volume. And a specific heat capacity is just taking the system, taking its heat capacity and dividing by its mass, that's all. Okay, we have now all the funny things we need for the formulas. Then there's something we call in physics perturbation. We call it sound normally. So when I speak to you, in fact, there's a perturbation of the atmosphere propagating to you with a velocity of around 340 meters per second. That's the temperature and density of the air, and this is the formula for it. So we recognize some things. There's gamma, this adiabatic index, and R, this universal gas constant, and T, the absolute temperature, and M, the mass of the substance the wave is propagating through. So to put it into perspective, gamma is always a number between 1 and 1.66, something like that. So it's a small number. And we had learned R is approximately 8. So gamma times R is approximately, I don't know, 10, 12, 15, depends on which gas you look at. And then you have a certain temperature. Okay, at the moment we have room temperature, 295 Kelvin or so, and then you have to divide it by the mass of the substance in gram. Okay, air has, I don't know, 28 grams per mole or so. You divide it, take the square root, and voila, there's your speed of the sound in air. But of course, you can do the same thing in a burning chamber. Then you have different materials, for example, liquid oxygen and liquid hydrogen burning. Then you have a different molecular mass, you have a different temperature, hopefully, but you can then calculate the velocity of sound in a burning chamber. And then very important is the so-called Mach number. This is just taking some velocity and dividing it with the local sound of velocity of sound. So if you are at Mach 1, you're just traveling at the speed of sound. Okay, and very important for gas expansion is, of course, the pressure a gas can exert on its environment. So let's look at this ideal gas equation, and don't think about atoms. Think about hooligans. You take n hooligans, put them in a confined space V, and agitate them with a temperature. Then they will exert a pressure on its environment. Okay? Yeah, you have to look at it that way. It's what happens. So you can write this formula in a lot of ways. So this way would be the physicist's way to do it. Maybe he would put V on the other side. Then this little n is not just, is just now the number of hooligans per volume. No? I don't know, hooligan per cubic meter or so. And this would be the way the chemist would write it. No? Number of dozens hooligans per volume. And this is also a chemic. This is a concentration. And in rocket science, you normally use this one, pulling the density to the other side. So this is a formula you very often see, and it's always the same. It's always ideal gas, very simple, stating that the pressure is always proportional to the temperature and inversely proportional to the space you confine the gas, and already the same proportion to the number of particles that are exerting the pressure. Very simple equation. So what can we learn from ideal gas? It simplifies a lot. First of all, this strange adiabatic index that no one here seems to appreciate is just the number of degrees of freedom plus 2 divided by the number of degrees of freedom. This is very simple. So if you have a diatomic gas having 5 degrees of freedom, you have just 5 plus 2 is 7 divided by 5, 7/5, 1.4. That's the adiabatic index of air, approximately, okay? And if you have, for example, pure hydrogen as monoatomic, like, for example, running out of an atomic engine, nuclear engine, then you would only have 3 degrees of freedom, and this number would be 5/3, so 1.666, something like that, okay? It's very simple in this case. It's just a number. And the difference between the two heats would be just the universal constant, 8.314, etc. And we can exactly calculate what the specific heat at constant pressure would be. So this helps a lot if we want to calculate what's now to follow. So what we do when we accelerate gas in a burning chamber is we expand it. It starts as a gas, very, very hot, very, very high pressure, and then expands through a nozzle. And we have to do some assumptions to reduce the complexity of the calculations. Okay. So, one dimension, steady flow. We don't look at time changes, so things like pogo, vibrations in a burning chamber, not at the moment. It must be adiabatic, so the process is so fast that no additional heat can flow into the gas. It must be isentropic, that is, no friction or otherwise, and no chemical reaction, so this is a very simple model. We use the ideal gas, as I mentioned. And the only work permitted is volume work. It is when the gas expands, it works against environment. So, and not so important, no significant changes in potential energy. Normally, a burning chamber is not that large. Yeah, it's like this or like that, and not 100 meters large. Otherwise, one had to look at the potential energy difference in the different parts of the chamber. So, the first thing one learns is about stagnation enthalpy. This is a constant of the flow. And this is a very, very important constant because it helps one to deduce all the formulas I will show you in a few seconds. It just states that there's a constant, H0, and it's constant for all the movement of the fluid throughout the chamber. And it changes only due to the fact that the fluid starts to move. Or the larger the motion, the lower the enthalpy of the element of fluid. So one can rewrite that and bring in the temperature. So that's a very interesting point because it has another application except for the formulas to describe the chamber the burning chamber. This is, for example, interesting when you are moving a rocket through air at a very high speed. Let's say V is in the order of Mach 2 or Mach 3. Then the points where you reach stagnation, it is where the air doesn't move, where air touches, for example, at the tip of the rocket, where the air is not moving, then you can calculate from this formula a temperature at the tip, and you will get very high temperatures above 3-4 Mach. So you have to build your tips and your other parts that are exposed to the flow that's running around, across the rocket. You have to build it from a material that can withstand the temperature you can calculate with this formula. So after these preparations, we now come to the device that really produces the thrust. And this is the little thing just below. This is the nozzle. And it was invented by an engineer called De Laval in 1888. He was building a steam turbine. And what essentially happens in a nozzle is that we get from the burning chamber with very high temperature and very high pressure, and then this flow goes through, and at the throat, as we call it, at the throat, the flow reaches exactly Mach 1. So it gets sonic. And when it leaves the throat, it gets supersonic. And that's the trick of this nozzle. So you get in with subsonic speeds, then you get sonic exactly at the throat, and then you leave at the end of the nozzle, you leave with supersonic speeds. So this is a diagram, what's happening in a chamber. So you have a certain pressure, the chamber pressure, and it exerts forces in all directions, only that it cannot go out there. The only way to go out there is the nozzle throat. So the flow starts to go through, and when it leaves the nozzle, the pressure has diminished. It is lower than at the starting point. Okay, there are formulas to describe it. I won't discuss that now. So we have now two contributions to the thrust that the engine will exert. The first contribution is due to the flow with the nozzle exit velocity, VE. This is the first term here, this one. And the second term is like a pressure difference exactly at the nozzle. Okay? So this pressure here might be higher or lower than the ambient pressure, and then we get an additional term. So that's how it happens. And this is the flow. So it starts slowly in the chamber, then gets to sonic speeds at the throat, and when it finally leaves the nozzle, you have an exit velocity that is supersonic. And now, beware, this effective exhaust velocity we talked before is not exactly equal to this velocity because of this pressure term. This pressure term will slow down or accelerate the gas that leaves the nozzle at this point, even beyond the nozzle. So, I talked about specific impulse for some time. This is the formula to describe, and it's the most important number, and I want you to memorize it. It's just the thrust divided by the mass flow times the acceleration of Earth. So G is approximately 9.81, but you can put it to 10. So the ISP is just the thrust divided by how many kilograms per second times 10. So for example, if this thing has 1 ton of thrust, your engine, and it pushes out 10 kilograms per second, okay? So it would have a specific impulse of 10 times 10, 100, what did I say, 1,000 kilopond, okay? So 10, not very good. So, and the effective exhaust velocity is just connected by G. So if you know that the velocity is, let's say, 2 kilometers per second, then the engine has an ISP of 200 seconds. It's just dividing by 10. So this is the formula to calculate the exit velocity. As you can see, there is the temperature here. It's proportional to the temperature in the chamber. So the hotter the chamber temperature is, the faster the exit velocity. And it is inversely proportional to the molecular weight. So the lighter the combustion products, the faster the exhaust. So this is where the engineers always try to optimize. Higher temperatures, lower molecular weight. And this here, you cannot optimize very much. So this is given by the reaction. This is this number between 1 and 1.66, depending on the combustion products. And this is given by the nozzle geometry, and you cannot change very much because it depends on the ambient pressure. So, and if you look at the formula, it's very close to the sonic speed in the burning chamber. So the exit velocity of a rocket engine is proportional to the speed of sound in the rocket chamber. This formula was invented in 1860 or so. It's very old. So this is the thrust. I won't go here into details. You just put in all the variables and you get the thrust of your engine. So you put in the area of the throat, the chamber pressure, your exhaust gamma value, the exit pressure, chamber pressure, etc., and then you get the thrust. It's just a formula. But now you know what these terms hopefully mean, and then you can calculate what it does. So let's talk shortly on the technologies that we can employ. So there are mainly 4 technologies that are today working. This is a cold gas, chemical, electric, and nuclear. Okay, some of you may think nuclear, never built ever a nuclear engine. Not true. There was a working nuclear engine in the 60s, and they tested it and it worked, and they wanted to fly it to the moon, but then they decided otherwise. So, as you can see, the lowest impulse, specific impulse, is cold gas. Then comes chemical, followed by electric, and nuclear is somewhere in between chemical and electric. So, but the problem is that the total thrust you can produce with these engines depends on the technology. So with cold gas, you can only produce something in the order of a few kilograms, kilopond. With chemical engines, you can go to hundreds of tons. With electrical engines, you can maybe lift very, very few, up to 2 kilopond, no more. And with nuclear, you are even with chemical engines. So what are the pros and cons of these technologies? For cold gas, extremely reliable. Very simple design. You only need a pressure vessel and a pressure reducer and a valve. Very safe operation, no contamination, no combustion, and precise thrusting. So this is especially for exerting torques, for example, for maneuvering, for very low impulse maneuvers. So contra is, of course, low ISP, low thrust, and you need a high pressure vessel, which can be very bulky and dangerous if you pinch it. So chemical is the way to go at the moment. It has high thrust. It's heritage, that is, we have a lot of designs to rely on. It has, unfortunately, a medium ISP, but enough to leave Earth. It has good mass ratio, but it's not inherently safe, as we have learned. It exerts high temperature, so that's one main problem in the design. You have to cool. There are combustion instabilities, sometimes. And of course, there's environmental hazard if you use chlorine or fluorine or something like that. So electrical engines have a very high ISP, which is very favorable. They are proven. We have flown to the moon with one. They are reliable, and they have a very good mass ratio. The problem is very low thrust, so you need a very long time to accelerate, and they have a high energy demand. So without something that generates the electric energy, you can forget it. So nuclear has very high ISP and high thrust, but it has radioactive exhaust, a little bit. It's not inherently safe, to say the least. It's at the moment politically unfavorable. Nobody will give us, like, say, plutonium, please. It's unproven in the sense that it has never flown, but there were working designs on Earth. And it has a very high dry mass, so you have to build very large rockets. I'm finishing now I'm nearly finished, so you can ask them. Please hold the question. So, this was the end. Thank you. So, by the way, this is a very good book. Read it.
Well,
yes.
Engineer would still need a propulsion medium. And in the design from the 60s that you spoke of, that's a Pluto missile, I believe.
I haven't heard of
that was more a torpedo than a rocket. It used medium. It used air as a medium. It propelled through air with an atomic reactor. But it still needs something to heat up.
I I don't understand the words. I'm sorry.
Okay. Is it?
Yes, it's hauling. Yeah, it's echoing. Yeah, better.
The atomic rocket or the atomic propulsion you spoke of. I believe that's the Pluto missile you spoke about. That was more of a torpedo than a rocket. So it needed an external medium, it needed air to propel through air, and it cannot fly in space. So
I understand.
Atomic engine, I believe you still need a medium that it can
Also,
fly.
as I understand, you are referring to Pluto, the military application of nuclear engines. This was an air-breathing nuclear engine, and it was tested, but this is a totally different program. So there were different programs to build nuclear engines. The NASA conducted one, and I think it was the Air Force that conducted the other one. I'm not very sure. And both were successful in the sense that they built a working design. So the Pluto cruise missile, as it called it, was built to take about 20 hydrogen bombs to Russia and to mess up the whole of Russia by flying at, I don't know, Mach 2 or Mach 3 at 50 meters or so and destroying everything in the way with radioactive exhaust and putting down the hydrogen bombs. So, and then they designed it in the 60s, and they tested the air-breathing nuclear engine. That is, this was a reactor that was cooled with air that was sucked in. So, and it worked. It had very little radioactive exhaust. They thought it would have more, but they only tested it for several minutes, 5, 10 minutes, or a few hours. I don't know exactly, but it worked. So it was working. But then the politicians said, no, better not. Let's do something else. Maybe the Russians would retaliate with something more ugly. Yeah? And the other project, the Project Nerva, which was funded by NASA, it started in 1948. There were the first memoranda thinking about nuclear engines. And they thought about 10 years about a feasible principle, and in the end of the 50s they started to build one testing reactor and several, I think about 4 different nuclear engines called Kiwi 1 and 2, and then the middle I forgot. This was something with Dumbo, yeah, something, the flying elephant or so. And the last one, the Nerva, was a working design. So they finished the design. It was ready to use. They tested this extensively. They even made a test with a Kiwi engine that exploded on purpose. So they made it super critical, and it just blew the sky open. I think I may have a picture of that. So this is the Nerva. Oh, shit. Sorry. So this is the Nerva reactor, and this was a working design. So you have here the turbo pumps that pumps the hydrogen into the reactor. Then you have a shield here to shield the astronauts, of course, due to the neutron radiation. It's very dangerous to be near this reactor. Then you have here the solid reactor core, neutron reflector, and then here the propellant line that will cool before entering the reactor. So this was working. This was not just a diagram. They had it ready. No, you're blowing the hydrogen out. You're cooling with liquid hydrogen. The hydrogen dissolves into atoms, and in the nozzle it connects, and then you reach temperatures of over 10,000 Kelvin, and you can get an ISP of, I don't know, nearly 1,000 seconds or so. That's the trick. No, the reactor stays in place. This is the solid core reactor design. Of course, there are different designs. There are with liquid core and gaseous core, but normally the fission material stays in place. Otherwise, the reaction would stop. Okay?
Are there any other questions?
You've already answered the first question of how would a nuclear engine work, and could you tell us a few words about the underlying principle of electrical propulsion?
I don't know why. I don't understand the word here. Up here.
Okay, I'll try it this way. So could you say a few words how electrical propulsion works in
Yes, yes, of course, of course. Let me see. There are different systems. One of the most advanced is so-called Vasimir. This is very promising. This is a copyright by some, there is a corporation that's trying to build this one. And it's mainly based on producing a plasma with RF power. So you ionize gas that is in propellant tank here. You ionize it with radio frequency. And then you use this plasma and boost it again with the magnetic field outwards. And this has the advantage that you can achieve very high thrust with low specific impulse. So you can launch from another celestial body. And then when you are going from planet to planet, you can increase the specific impulse. But the problem of this, of every electrical engine is, of course, the power. I'll show you, I'll see if I have another one. No, not at the moment here. Sorry. No, let's see what I have. So there are a lot of principles to build an electrical rocket. There's an arc jet, resistor jet, there are Hall thrusters, electrostatic thrusters. Every one of them has certain advantages and disadvantages. But all of them have the disadvantage that they need electric energy in large amounts. So otherwise, you have large solar sails, that's one possibility, or you have to take with you an RTD, a nuclear battery, or even a nuclear reactor if you want to really go fast and far away. Louder.
It's not possible without the mic, sorry.
Okay. About the Vasimir 200, it's the 200 stands for 200 kilowatt and it gives 100 Newton away. And a friend of mine and I did look into this technology, and the last test endured 4 hours. Then this antennas they're using to couple this higher frequency, HF frequency, into the plasma burns through. You don't understand the word.
The acoustic is terrible here. I hear everything out, but not what is spoken here.
Well, when I use the microphone, no one
Okay,
understands.
my suggestion is if you have a question, please come up here
come up here and
to the
speak to
speaker,
me, then I
use the
repeat it because
microphone,
it's impossible.
but he can understand you without the microphone. Come in front with the microphone, please.
Okay. What is the point about the microphone if you
That attendees can understand you, not only the speaker.
What?
Come to me,
Aha. Okay.
I cannot hear anything.
speak here in front so he can hear you directly,
Acoustic,
and
that's
all the
fine.
people can hear you through the speaker.
Aha. Okay. Well,
Use the microphone.
now the microphone.
So
Okay.
the other one here. I can't hear.
Okay. Someone mentioned Vasimir, and I'm in this project. I'm following the project
Yes.
since a longer time, and the last test had a duration of 4 hours. After this, the antennas they are using to couple the high frequency into the plasma burns through because of the impedancy of the antennas. And I had the idea to reuse magnetrons from an old microwaves because there was a successful test of producing a plasma torch with normal magnetrons, and it was a really incidental positive that I exactly drew this magnetron of the broken microwave which was used in this plasma torch experiment. And my idea was to use this magnetrons in combination with a waveguide to produce the plasma instead of coupled antennas which have a direct contact with the plasma and burn through after some hours. And we are building some little Vasimir, we are going to build a little Vasimir in our hackerspace in Zurich.
That's cool.
And
Interesting.
but as I calculated, it will only give some millinewton because we have some fuse which are only which limits the power. You can't draw 200 kilowatt. It will be some around 1-2 kilowatt because of the magnetron which draw.
It's the main problem of electric propulsion. It's very energy hungry, and there's no really turning point. You need an energy source that is really large, otherwise it doesn't work.
Maybe I will take some trip to, well, let's see, somewhere Russia near the sea, and watch out for all the submarines.
The Russians had a working reactor design, and they employed it in satellites, so they have this stuff somewhere lying around.
Well, if someone has a second-hand atomic submarine, he doesn't need anymore, I'll take it.
Okay, the last question, please.
Do you see any advantage in using a nuclear-powered electrical engine instead of a nuclear engine?
Advantage over what?
An advantage over a nuclear engine.
Who has
Where you-
advantage?
where you,
Electrical.
A nuclear-powered electrical engine, where you have to take a nuclear reactor to
Yes,
power
yes, it would have, if you choose the right electrical engine. The thing is, the thing is the specific impulse. You can reach with electrical engines very high specific impulses up to 10,000 seconds or more. The problem is that you need, the more specific impulse you want to have, the more power you need. So you're always power dominated. Yeah? If you have more power, you can go faster. The thing with nuclear engine is that you have very high thrust. So if you are moving through the gravitational well of a planet, for example, and you want to get out, then electrical propulsion has at the moment, because of the very low thrust it can exert, has the problem that you have a lot of gravity losses. So you need almost double the delta V to achieve the same mission. So for example, with SMART, that went directly to the moon, you didn't use, like with chemical engines, I don't know, a delta V of approximately 7-8 kilometers per second from Leo, but the double, okay? So this is a problem if you have very low thrust. And the only engine I know that has higher thrust is Vasimir, but it has problems with the energy demand and with corrosion and so on, but they're trying. They're trying. Okay, that answers the question?
Okay, thank you, David, for your talk. What was very interesting. Do you maybe have a contact for people who might join you for a discussion afterwards, a tent or?
Sure. Well, I don't know exactly where we are located. We are in the furthermost. Welche? We are in outer space. Very good. We are in outer space, and we are the big blue tent, and we have rockets there. Lots of rockets. So come and see. And we have avionics there, so programmers are welcome. And we can always use a helping hand and someone who looks at our hardware to comment on. So please come.
Okay, so thank you all, and little applause for